For more videos like this for Discrete 1, you can take a look at Sarai Studies, link is in the description box below. We're told to prove that if n squared is even, then n is even. First things first, the domain, they don't tell you, but you have to use the context of the problem. The only numbers that can be even or odd are integers, so the domain that we're working with is a set of all integers, which we represent with this symbol, a z and an extra line. The second thing you want to do, no matter what proof you're doing, is your definitions. What does it mean for an integer to be even? Well, we can say an integer s is even, so this integer could be any variable you want, r, t, q, whatever. I'm just going to call it s. If and only if, so we use the double implication operator. There exists, so we use the there exists quantifier. A k, where k is an integer, k is an element of, so this weird e for element of the set of all integers. In other words, k lives in the house of integers. In other words, k is an integer, however you want to read it, such that, so this k is restricted by, it's subject to this condition where k needs to multiply by a 2 and should give me this integer that is supposedly even. Now, if you want to know why this is true, I explained it in this video. It's the first video under direct proofs on Sarai Studies, so you can check that out if you want to. So because I see an implication, this is really an if this, then this statement. So I can try doing this proof by a direct proof, because a direct proof says, well, if we call this proposition P and proposition Q, then we can assume P, and then we can use axioms, theorems we've already proved, known equivalences, definitions, properties, and so on to show that Q is true. So we can try using a direct proof first. So let's see what happens when we do that. So we first start by assuming P. What is P? N squared is even. So we're assuming that n squared is even. What does it mean for n squared to be even? Well, first of all, is n squared an integer? The answer is yes, because with a direct proof, we start by assuming P, and the only thing that has a property of even or odd are numbers, and the only numbers that can be even or odd are integers. And so if we are assuming that n squared is even, then therefore we are assuming that n squared is also an integer, because only integers can be even or odd. In other words, we have an integer that is even. And what do we know about an integer, let's say n squared, that is even? Well, this definition says that if this side is true, then we say that this side is true. And what does this side say? Well, it says that there exists an integer k, that if you take k, multiply by 2, it's going to give you that integer that is even, n squared. So in other words, because we are assuming this is true, then this is true. N squared is equal to 2 times an integer k. So this implies that n squared is equal to 2 times an integer k, where k is an integer. Now we assumed p, so we're over here, but we're trying to show q. So we have to say something about n. So the idea is we have to somehow go from n squared to n. So maybe I can try square rooting, because to undo a square, I have to square root. So these cancel out, I'm left with n, but whatever I do to one side, I have to do to the other. So then this ends up being n is equal to the square root of 2 times k. And by the way, the step we used here was the definition of an even integer, and the step we're doing here is simply algebra. So now we have something to say about n, but what we want to say about n is that it's even. And what do we know about an integer n that is even? That there is some k that is an integer that will multiply by 2, and it's going to give us n. So if we want to show that q is true, we're going to have to show that n is equal to 2 times an integer k. But right now what we have is that n is equal to the square root of 2 times some integer k. And no matter what you do, you're just not going to get it to look like this. I mean, you can take the square to get rid of this, you end up with 2k, but whatever you do one side, you have to do to the other, so you end up exactly where you started. So we're stuck. A direct proof did not help us. So then we have to try another method. So instead of a direct proof, we're going to try another method called the contraposition. And it's actually the same thing as a direct proof, except that you're not proving the original statement P implies Q, you're proving the contrapositive of P implies Q. And it's easy to remember because contraposition and contrapositive sound really similar. I like to think of it as when I'm doing a proof by contraposition, I'm in the position to use the contrapositive. Now, if you don't remember what a contrapositive is, it was introduced when we started learning about the implication operator. So when we have an implication of P implies Q, the professor can ask you to find different variations of this implication, like the inverse, converse, and one of the variations is the contrapositive. And the contrapositive of P implies Q is not Q implies not P. So you can memorize this, or you can go to Sarai Studies under the propositional logic section, scroll all the way down until you see variations of the implication operator. I did do a video, so if you click on it, if I showed a little phrase that can help you remember what the converse, inverse, and contrapositive of an implication are, so you don't ever have to memorize it. So you can watch that video if you find it helpful. The link to the website is in the description box below. But moving on, so the first step with a proof by contraposition is to find the contrapositive of your original implication. And we know that the contrapositive is not Q implies not P. We know that Q, its N is even. Not Q is going to be the opposite of N is even. So what's the opposite of N being even? Well, N being odd. So this is going to translate to N is odd, implies, and then P is N squared is even. So not P is going to be the opposite of N squared is even. What's the opposite of N squared being even? Well, N squared being odd. So not P is going to be N squared is odd. So the way to approach this is to imagine as if this is what they gave you in the first place to prove. And then what would you always try first? A direct proof. So you're literally just doing a direct proof on the contrapositive of your original statement. So we can move this over here and say prove that if N is odd, then N squared is odd. So with a direct proof, we assume that P is true. So notice how I'm not saying that this is not Q. I'm literally treating this as if I'm seeing this for the first time. It's just a regular P implies Q. I just use this to get to here. It's like I'm starting like this, okay? So this is my P, this is my Q. With a direct proof, you assume that P is true. But what is P? P is N is odd. So this is interesting. We have a new term. Before, we just needed the definition of an even integer. But now we have to define what does it mean for N to be odd. So I'm going to move this below here, and I can actually copy the definition of an even integer, and all you have to do is add a 1. Do you know why? Because think of the first 3 even numbers you can think of. What happens if I add a 1 to them? 2 plus 1 becomes 3. 4 plus 1 becomes 5. 6 plus 1 becomes 7. If I have an even integer and I add 1 to them, they become odd. So the definition of an odd integer is the definition of an even integer plus 1. It's even integer plus 1 will always give you odd. So all you're doing is just adding 1 and changing this to say odd. Now back to this. If we assume that N is odd, so assuming P, what does this imply? Well, if N is odd, so if this side is true, then that means that this side should also be true, that there is an integer K, that if you multiply by 2 and you add 1, you get N. So if this side is true, we're assuming that this side is true, then this side should also be true, that N should actually be equal to 2 times some integer K plus 1. So this implies that N should be equal to 2 times some integer K plus 1, where K is an element of the set of all integers. In other words, K is an integer. So what we used here was the definition of an odd integer right here. So right now we're at P, but we want to get to Q. We want to show that Q is true. But Q says something about N squared, so we have to say something about N squared eventually. So the question is, how do we go from N to N squared? Because all we have is N. Well, you can literally square N, but whatever you do to one side, you have to do to the other. So with some algebra, we have N squared is equal to 2K plus 1 squared, and this is still equivalent because I did the same things to both sides. So now I'm finally saying something about N squared. But what I want to say about N squared is that N squared is odd, but right now what I'm saying about N squared is that I have something squared. And is that the definition of an odd integer? No, the definition of an odd integer is 2 times an integer plus 1. So I have to get this to look like this so that I could say that N squared actually is an odd integer. So all I can do right now is actually square this entire thing. So I know you're tempted to square this, and you know what? Go ahead and do that. Let's do that. Let's square this, square this. When you're squaring terms instead of factors, terms are separated by addition, subtraction, factors are separated by multiplication and division. So you can't just like square each term. You also have to take care of one more thing. You have to add 2 times the product of the terms. So 2k times 1, which is just 2k in this case, and you're adding everything else. So to simplify this becomes 1. This becomes 4k. And then here you can see the difference. With these, because these are factors, 2 and k are factors, are separated by multiplication or division, in this case multiplication, you are allowed to square each factor. So 2 squared becomes 4 and k squared becomes k squared. So with some algebra, N squared is equal to 4k squared plus 4k plus 1. But again, I want to say that N squared is odd. So if N squared is odd, then N squared should be in this form. So I need to somehow get a 2 out here. here. And what I notice is that I have 4's here, so I can factor out a 2, and I'm left with k squared plus k. This 1 drops down, and so I'm left with this implies that n squared is equal to now 2 times something plus 1, again with some algebra, which is very similar to the definition of an odd integer s that's equal to 2 times something plus 1, but that something is an integer. Is this an integer? Well, the answer is yes, due to the closure property of integers under addition in this case, because these are being added, and actually under multiplication too, because this here, recall that k is an integer because we specified it here. So the idea is when you do k squared, it's really just multiplying k by itself, and the closure property of integers under multiplication just says if you multiply 2 integers, you're going to get another integer. So this is an integer, and then the closure property of integers under addition says, well, if you add 2 integers, which we know this is an integer because we specified it here, then you're going to get another integer. So we can call this integer r, whatever you want to call it. I'm just going to call it r. So this implies that n squared is equal to 2 times r, and then you can bring down the 1. And what we used here was the closure property of integers under product and sum. That allows us to say, yeah, if you add and multiply integers, it's still going to be an integer. This whole thing is just going to become an integer. And we want to specify that r is equal to this, k squared plus k, and r is also an integer. So now I have that n squared is equal to 2 times some integer r plus 1, which is exactly the definition of an odd integer s, 2 times an integer plus 1. So because I managed to define n squared as an odd integer, then using this definition of an odd integer, this implies that n squared is odd. Because what we're saying is if n squared can be defined as 2 times k plus 1, so k can be any integer, it could be r, whatever you want to call it, then if this side of the implication is true, then this side must also be true. So an integer n squared is odd, so therefore we can conclude that n squared is odd. And that is exactly what we wanted to show. So we managed to go from p to q, from p all the way to q using definitions and properties and such. Then for a conclusion, we say therefore, because that's what the symbol means, and then you copy and paste exactly what they wanted you to prove. N is odd implies n squared is odd. Now zoom out. You have to remember that the original statement that you had to prove was this, but you only proved this. So then what is the connection? Why do a proof on something that's completely different than what you wanted to prove in the first place? Well, the reason is because it's not completely different. This is actually the exact same thing as this. You have to remember a nice key fact. The original implication, the OG implication, P implies Q, is equivalent to the contrapositive, not Q implies not P. Meaning that if this is true, which we found it was true because we proved it, then the original implication is true. So that is the connection. Because of this fact, we know that P implies Q and the contrapositive not Q implies not P have the same truth values, are equivalent, meaning that if this is true, then we can say that this is true, and if this is false, then we can say that this is false, and vice versa. So to finish off our conclusion, this here, right over here, is the contrapositive not Q implies not P, and we found that to be true. We proved it. So we say since the contrapositive is true, then by proof of contraposition, we can conclude that the original implication P implies Q is also true. So we just write this right over here, and that is it. We're done with our proof. So we write our little box to show that we're done, and that's it for this video. I'll see you in the next.